Welcome everyone for today's quantum space-time seminar. We are very happy to have Shreya Vardhan from Stanford University, and she's going to tell us about entanglement dynamics from Universality. So, over to you, Shreya.
Okay, great. Thanks a lot for the invitation. It's always a pleasure to be here. Today I'm going to be talking about this recent work with Sanjay Mudgalia. And the subject of this talk is thermalization in quantum many-body systems. So let me start with a sort of informal definition of thermalization, which is that if we start with some initial state, rho 0, and then evolve it with the unitary thermalization in the system, then this time-evolved state at sufficiently late times resembles some equilibrium state, rho equilibrium, which could be something like a canonical ensemble or microcanonical ensemble and so on. And remarkably, this process happens in a variety of essentially all generic chaotic quantum many-body systems, irrespective of details of their microscopic dynamics. And this is something that we take for granted in our everyday lives, but the mechanism by which this happens is still not well understood. Of particular interest to us in this room is the case of holographic CFTs, which are one example of highly chaotic systems. And in these systems, the process of thermalization in the boundary CFT corresponds to the process of black hole formation in the bulk. So understanding the mechanism for thermalization in the boundary CFT can help us understand somehow the microscopic mechanism for black hole formation. Okay, so the central question of this talk will be that if systems with very different microscopic dynamics show the process of thermalization, then how does this universality emerge? So what is the common underlying structure across all these different kinds of quantum many-body systems, which leads to this process? Okay, so when I say that the time-evolved state starts to resemble the equilibrium state, we can probe this using a variety of different quantities. So one conventional thing that we're very used to is to consider the expectation value of some few-body operator in the time-evolved state. And for such quantities, the statement is that at late enough times, these will have some saturation value, which will look on average like the expectation value of the same operator in the thermal state. Okay, and another set of observables, which has become very standard at this point, is to look at information-theoretic quantities, such as the Renyi entropy, which can be defined in this way. So if we have some subsystem A of the whole system, then we use the reduced density matrix, rho A, of the time-evolved state in that subsystem. And we can define this quantity in this way. Okay, so this quantity is a more fine-grained probe of the structure of the time-evolved state, and it can be seen as a measure of the correlations between A and its complement A bar. Okay, and for the Renyi entropies, the late time saturation value is expected to also be determined by the equilibrium state. So for instance, if our initial state was a pure state, then we generally expect an expression like this. That at very late times, the Renyi entropy will have a form which looks like the minimum between the Renyi entropy of the equilibrium state in A and the equilibrium state in A1. Okay.
So are you evolving your system from one equilibrium state to another equilibrium state or starting?
No, I'm starting with some completely out of equilibrium state generically. So for example, I could have some initial pure state psi 0, which is also a product state between different sides of the system in a lattice system. So that is a very atypical state, very different from rho equilibrium. But the statement is that even for such states, if you evolve to very late times, then it starts to look like the equilibrium state. Okay, so for yeah.
Are we also requiring that these approaches are up to, I mean, the corrections are really exponential, the minus entropy or?
Right, so this, you mean for the late time value?
Yeah. That's
So the late time value is extensive in the volume of the subsystem, and I'm ignoring everything that is not extensive. So for instance, area law corrections, logarithmic and volume corrections, and so on.
But the rate at which it goes to that
Yeah, that's exactly what I'm talking about next. So, this is the statement for very late times, and this is still somewhat relatively well understood. So this is something that I had discussed a year and a half ago when I gave the talk, how you can understand some general microscopic mechanism for the emergence of this late time value.
So Shreya, so the A stands for your system and A bar is the entire complement.
Yeah, exactly. So I'm imagining.
So the A in union A bar evolves in a unitary way.
Exactly.
Or the evolution is also unitary, separate unitary, because there you write your U dagger on A itself or
No,
this
no.
evolution.
This is the whole system. So U is general unitary matrix A bar.
So rho naught is the full density matrix.
Yes. Yeah. So I could have just considered the case of a pure state on the whole system. More generally, I can consider a mixed state.
Okay.
Yeah.
So a dumb question, what is the significance of that minimum identified?
Yeah, so the minimum is important because I said that I'm considering the case of an initial pure state. And by unitarity, because this combined evolution of A and A bar is unitary, I need to always have the constraint that the entropy in A is equal to the entropy in A bar, which would not be obeyed for the equilibrium state by itself. So this was a sort of non-trivial insight from Page, where he did a calculation for random pure states. And he obtained a version of this formula, which was like minimum. So he had this kind of setup in a finite dimension Hilbert space. The dimension of A is BA, dimension of A bar is BA bar. And he obtained a formula which was like minimum of log BA, log BA bar. So that is for the case of a completely random pure state. More generally, in a finite temperature system, you expect some expression like this. Okay?
Do you have in mind A is order 1?
No, not at all. So if B is the volume of the whole system, then I'm assuming that BA and BA bar both scale with the size of the system.
Then don't you expect generically that for the thermal state S7 and A bar is larger? A is order 1?
No, sorry. I'm assuming that.
Not order 1, sorry. A is much smaller, don't expect the other entropy to be larger.
No, I'm including both cases that either A is much smaller than A bar or A bar is much smaller than A.
I think if A remains order one, there's no problem anyway, the minimum.
Yeah, then we can just.
Yeah.
I'm asking, do we expect thermalization in this sense for A that is very large?
Yes, in this formula should apply even if A is bigger than half of the system. Does that answer your question?
I
So
like
this
this
is-
solution, but yeah,
This is stronger than usual sum.
Yeah,
The normalization.
it's a very strong form.
Yeah.
Right, so the motivation for it comes from partly from Page's calculation, where he showed that if you have a random pure state on the system, then this formula is obeyed. And we expect that the state that is produced by some chaotic time evolution at late times should be some slightly more constrained version of the random pure state. So in this earlier paper on the equilibrium approximation with Hong, we give sort of more systematic argument for where this expression comes from. And it's like some version of these replica wormhole contributions, so this is the Page curve in the black hole context, right? And you can identify these replica wormhole geometries in the black hole context, which give this second contribution. And you can also identify an analog of that contribution in any quantum many-body system. So that is what we are looking for.
So yeah, the initial state is assumed to be pure here or not?
In this expression it is, but it's not very important for the rest of my talk.
That explains why there has to be that term also, right? Because even though your system is bigger, its entropy could increase as much as the smaller one, right?
Exactly. So this ensures that at all times S and A of T is equal to S and A bar of T.
Right.
Okay, but this expression is not very important for the rest of my talk. The main thing that I wanted to emphasize about it was just that at late enough times, the entropy is fully determined by the thermal state. So for the pure state case, it's given by this expression. More generally, it would be given by something else, but that would always be determined by the equilibrium state. Okay. But we also expect that in chaotic quantum many-body systems, we have a universal behavior, not just of this late time value, but also of the way in which it's approached.
So how does the T comes? This T comes from the unitary evolution in time or something?
Yeah. So for example, I'm assuming that U is e to the minus IHT. Good.
Sure, sorry, one more thing about the minimum. So if A bar is very small compared to A.
Yeah.
So that the path is much smaller than the system.
Yeah.
then it's indeed a little unintuitive. For example, one extreme could be that the path is not there, and A
Yeah.
is the entire system.
Yeah.
In which case, if you start with pure state, then of course it does not equilibrate. So presumably there's some some assumption that goes in about the relative sizes of A and A bar. Even if A bar is smaller than A, presumably it's still extensive or something like that.
Well, not as in the particular case that you said, the log of the A bar would just be 0, right? So, in that case, the minimum would just give you 0 between these two terms.
If I start with the pure state, then I see, then it's the lower formula.
Yeah, it's the minimum of whatever these two terms are. So, oh, sorry, either of these applies. But either of them, in the case where you shrink, so you wanted to take the case where A bar is the whole system, or you want to take the case where A is the whole system and A bar is
Yeah, the path is vanishingly small.
it's vanishingly small, then this dA is 1, so this just becomes 0.
E solves the path.
Yeah,
I see.
then E is the path.
So basically, in that case where
Turning around.
But Shreya, you don't expect the entropy of the system to depend. Well, okay. I mean, to depend on the fact that it started as a pure state, right? Even if the initial state was a mixed state to begin with, and you after some time you expect it to equilibrate, and for that, what kind of formula will you write down?
So you get some generalization of this formula, which involves sum over. So we can consider one extreme limit of that, where you already started with the mixed equilibrium state. So in that case, you should just get just this one contribution. And then more generally, you get something intermediate. So I don't remember the exact formula, but you can write something down. This was also discussed in this paper.
Is it fair to say that this is really coming from the intuition of Holographic?
No, that was more because no, I don't think we should say it's coming from the intuition from holography. It's coming from the intuition that this is the most natural thing that is consistent with both thermalization and unitarity. Because unitarity requires that it should be symmetric between A and A bar, and then thermalization requires that it should be given by this expression for A less than A bar. So yeah. Okay, great. So what I want to focus on in this talk is the universality in the way in which the equilibrium value is approached. And for observables like these, like correlation functions of few-body observables, it's well understood that it's been known for a long time that there is a universal behavior in how they approach their late time values, and that is governed by some hydrodynamic modes. So these correlation functions will show some hydrodynamic behavior at late times. And more recently, in the last decade or so, it has also been understood that there is a universal behavior in the time evolution of the Renyi entropies. Okay, so this is an understanding which is developed from both study of chaotic spin chain systems and from holography. And all of these observations were synthesized in a so-called membrane formula. By Integrated Renyi using okay, and so they discuss this for a certain specific systems, and my goal in this talk is to try to understand some common underlying structure across a variety of different microscopic systems, which will lead to this membrane formula. So let me first review what the formula and the conjecture is.
Shreya, the dA and dA bar could both be finite size for this formula to be correct?
Well, we need to be careful about one particular case where the ratio of dA and dA bar is 4 to 1. So I assume that that is not true in this expression.
Yeah, otherwise it would be sort of analytic looking.
Yeah, exactly. Yeah. Right. So let me review this membrane formula. So I'm going to state the expression for a case where I have, so in this whole talk, I'll be considering systems which have some local chaotic interactions. And I'm interested in finding the evolution of the entanglement entropy in one spatial dimension for a half-line region, which is to the left of some point x. Okay, and I want to find its time evolution, so I label the time involved and training entropy, Sn x x and t. And the formula by Jonah says that if we want to find the time evolution of this expression in some chaotic system, then first extend this system in the time direction from some auxiliary time tau equal to 0 to tau equal to t. And then consider all possible different lines with different velocities. So we have some endpoint at tau equal to 0 here, y, and d is minus y over t. And then the expression of entropy is given by a minimization over all possible velocities of some linearly growing term in time, which looks like this. So I'll explain what this coefficient is. And then some initial entropy contribution coming from the entropy up to y. Okay, so and in this expression, so Sn equilibrium is the entropy density of the nth Renyi entropy in the eventual equilibrium state, like in this formula. And this function epsilon and v is sort of the key input. So this is in general a model-dependent function, but the statement is that it always has a shape which looks like this. It's a function of v. So it's some even convex function, and so this is the 45-degree line on the YV axis, and so this function obeys certain general constraints. So you know, epsilon and v for any v is greater than or equal to v, which is just a statement that this curve always lies above this line, and then epsilon n of a particular velocity vb is equal to vb, and epsilon n prime vb is equal to 1. Okay, and these two together are just a statement that this curve becomes tangent to this 45-degree line at some point, and then I call the velocity at that point vb. Okay, so
And for 5 dimensions, it's like a 4-dimension 1.
exactly. So for a higher dimension, say I have some region A in 2 spatial dimensions, then I should consider some 4-dimensional surface like this. And then again, I get some initial entropy contribution from this region, and then I integrate a function of the absolute value. So at every point here, I have some velocity vector. So I integrate the area of this surface times, and then I have some integral over that times dt times some function epsilon and v of the absolute value of v.
Sorry, what does x of n x? You mean what
Yeah,
does x
sorry,
mean?
it's the entropy of this region to the left of x at time t under some evolution like this.
This is true for any initial state.
This should be true for any initial state.
The input is coming there, I guess, in the second term, right? That's the
Uh,
Sn x minus Vt, that's the entropy of the state evolved backward in time.
exactly, yeah. So this is the empirical unit state. Also, if you consider very different initial states, then the equilibrium entropy density could be different. But this function should be the same.
Sorry, Sn is a finite with infinite. So just a half infinite line.
Yeah, it's infinite, but I'm imagining regulating it in some way. Like I have some, say I label the positions on the system from minus L over 2 to L over 2. Then for most purposes, I'm just interested in taking L to infinity. But yeah.
So yeah. So you're thinking of delta Sn as a function of time there?
Sure, yeah.
Sorry, could you? So that E and V is some sort of velocity. Sorry, could you say intuitively what's going on? What this is?
Well, that will be partly the point of the talk. The statement so far is this is some function. You can obtain this some function like this for any chaotic dynamics. And
So given the function, however I got it,
yeah,
it's giving me the rate at which this
Good.
Sn equivalent spreads.
yeah. That so I wanted to do a couple of examples to give you some sense of what this formula means.
You also say how they arrive at it?
Yeah, so I was going to mention this later. So they arrived at this by first from studies of random unitary circuits. So in that case, you do some calculation where you have a spin chain system, like some finite dimensional Hilbert space on each side. Then you, as a very simple model for a sort of maximally chaotic evolution, act with two-side random unitaries, first on this pairing of sides. And then on the other pairing of sides, and then keep doing this. So this is like a sort of plotterized model for a chaotic spin chain evolution. The nice thing is that if you take these to be drawn from the random ensemble, then this calculation of the entropy in this case maps to some classical partition function using the random average. And then you can calculate the answer. You can find that it takes this form for some non-trivial function x naught. So that is one example. Then the intuition is that these are very similar to generic chaotic systems. And also the remarkable thing is that the evolution of the entanglement entropy, the von Neumann entropy in holography can also be written in this form. So this is shown by Marcuse.
And min over what?
Min over velocity. So different lines like this.
And if there are spatial homogeneities in the Hamiltonians, we have a minimization or passing curves.
Oh, if there are inhomogeneities in the Hamiltonian, then probably you don't get some simple specialties.
You don't expect it to be like a minimization over curves. More like not just
Yeah.
straight lines, but more.
Probably at least that, but also like maybe the function depends on which point you start at, right? So
you're probably going to say this, but what I'm reading from this formula is that you've got like a wave front, which has reached VT. Once you've reached VT, the entanglement entropy before VT from x minus VT and less is unaffected. And that region is replaced, that wave front region is replaced by SNE ENVT. Is that correct?
So I was thinking of the entanglement propagates, right? Entanglement propagates in classical way.
Yeah.
Because you minimize it.
Yeah, somehow the result is that it looks like it's propagating in a classical way. Let me give you some, let me try to give the examples I was mentioning and then maybe that'll. But I think your intuition is correct. Sorry.
Just one quick question. So if you have like 1 plus 1 CFT, does it reduce to the Scalabrese party?
No, it does not, because for that, yeah, so if you just look at a half-line region like this, then you get the same result for both quasi-particle picture and chaotic systems.
Okay.
But if you look at the case of multiple intervals, then there's also a version of this formula for that case. So in that case, you should you have to consider cases where you have individual measurements reaching the t equal to 0 slice from these 2 points, endpoints of the interval. Actually, even for a single interval, the result is not different. Let's say I have 2 intervals. Then I have cases like this, but I also have to include other configurations where the membranes can combine like this. And then I minimize between all of them. So that gives me a formula very similar or the same or some very natural generalization of the holographic formula in 1 plus 1 dimensions.
Sorry, they came up with this formula by looking at this random tensor model. How do you see minimization over V in this random tensor? Because the intuition of this, like holistic sort of wave moving, I understand, but where's the minimization in that picture?
Okay, let me very briefly mention that. So in that model, so especially with the same geometry as the network, you can map the entropy to some partition function calculation on some lattice, which is also extended in this direction. So in that lattice, you have the like kind of similar to this random tensor network homologically. Anyway, so on that you have contributions from different kinds of domain walls. So you have a domain wall at this boundary, which is extending to the above. And the key thing is that if you're taking a great time limit, then you only need to look at like all of these contributions will be suppressed in T by different amounts. So if I consider this domain wall configuration versus some other one, then they will come with e to the minus something times 3. And you only need to take the dominant in T contribution, which will give you the minimization.
There's some sort of phase transition there, and that there are these are different.
There are large
Sorry, I should say this formula is not expected to fly at very early times, only after some intermediate time scale.
I meant large D.
Large D?
D is in the bond dimension.
No, it's not necessary to be the large D.
And sir, is function you are considering to be modular because these three conditions.
Yeah.
There is more.
Yeah, I'm assuming that. So I'm assuming that it's increasing with.
Because it can traverse that, right?
Yeah, I think these conditions are not sufficient for that, but it is true that it's always an increasing function and it's also always convex. So I think that. Okay. Yeah, it should apply for, so yeah, it should apply some scaling limit, where the size of the region that we consider is large, which in this case it's always large because I'm considering a half-line region. More generally, if I consider an interval, then I want the size of the region to be large, and T to be large, and the ratio of T and R to be a polynomial.
So at some point it will saturate or change behavior, right? Because the rest of the system starts becoming smaller.
Yeah. So if I indeed have a finite system, then at some point I have a case where the membrane reaches the endpoint of the system, and then it saturates. So yeah, that gives you that answer that I mentioned before.
Or in the case of the finite interval, they're looking at the entropy of the finite interval.
Yeah.
It's the point that the membrane just caps on.
Yeah, exactly. So there you get some configuration like this.
Yeah.
Yeah. Yeah.
So you said this, where does the word membrane be used here? What is the membrane in this?
The membrane is well, this line in one dimension, in one spatial dimension, and co-dimension two surface, and more generally, co-dimension one. One. Yeah. Okay. Okay, so let me give you more intuition for what this formula means. First, just consider the case where we have an initial product state. Okay, so then there is just no initial entropy contribution at all. So then the minimization over this function is very simple because I said it always has its minimum at b equal to 0. Okay, so in that case, I just get linear growth of entanglement entropy with a coefficient determined by the minimum of this, and that can be identified as the entanglement velocity for those who are familiar with the terminology. It's just some word, it doesn't matter.
So sorry, the fact that this has this second derivative, positive second derivative, is that an assumption?
That turns out to be true in all the cases where it's been studied.
Part of the proposal.
Yeah, it's part of the proposal. It's important for certain things.
Is there an intuition of why?
I guess. Well, one consequence of it is that I'm only considering straight lines here. More generally, I should have considered something like some curve like this. But it turns out that because of this convexity, the straight lines are sufficient. Which you can see by just considering a particular case where you have some change in velocity like this. So it's somehow more natural for a line tension to be convex. But I think there's only some vague reasoning related to it.
So E of 0 then is the front velocity in this case.
The E of 0 is the front, yeah. Well, per product state.
For the product.
But then the more general thing to consider is to take some initial state, which has an initial entropy density of some general S, where S is between 0 and S equilibrium. And then for such a state, you get a non-trivial minimization here, because by this I mean that the S of y at t equal to 0 is equal to some coefficient small s times y plus m over 2 in this case, because the endpoint of the system is at m over 2. So now when I plug this into that formula, then I get some v dependence in the second term as well. Right, so like this becomes minus s v t, So now I'll get some non-trivial minimization. And so I'll end up probing other parts of this function. And eventually, if the state that I start with already has S equal to S equilibrium, then its entropy density should not grow further. Because we're already starting with the equilibrium state, it should be left invariant by the time evolution. And that is ensured exactly by these two conditions for some BB. Okay. So the statement is that as you start with initial entropy density 0, then you start increasing it, you take larger and larger velocities, and eventually you have B equal to BB. And then beyond that, the velocity, this function is not relevant for the entropy evolution. Yeah. Okay.
Sorry, at late times, does V become VB always?
Yeah, good point. So if I had a finite region, then that's true. But if I want to compare the, so I have to compare in that case between two configurations. One where I have some general velocity reaching this point, and then another where the membranes combine. And it turns out, so I have to, so among all of these configurations, the straight line one wins, assuming that I have a product state. So I have to compare between this and this configuration. And it turns out that if you use all of these constraints, then you'll end up with the fact that if these lines are going with velocity VB, then this will give a contribution like S equilibrium times the length of the region.
So just to make sure. So I'm not talking about saturation.
Oh.
Let's say it's half line.
Okay.
Okay, so there's some entropy density on that side, some entropy density on this side.
Yeah.
And then I just wait for times that are long compared to, I don't know, 1.
Oh.
Then what's confusing me is this, that the reduction of entropy is growing at speed V.
Yeah.
Whereas the increase of entropy is growing at speed E. And I would have expected those to be the same, at least at late times.
I think that this term will not be. So, like you don't get a sort of continuous saturation of the entropy for this formula.
So it's not happening that, what I thought is that you're going to get whatever entropy you had being replaced by whatever entropy will be in equilibrium over some region.
No,
So that's wrong.
so what the formula predicts is that you have a sharp linear increase with some velocity given by some gamma of S, which will be determined by this minimization. And then, so at this point it's like gamma of S times T, and then it saturates to the equilibrium value. So it's not, at least at the level of this formula, it's not capturing, in particular systems, there could be some like more smooth behavior here. But this is not capturing that.
Well, let me ask again, I'm sorry, because I'm probably not understanding correctly.
Yeah.
So Sn of, when you do Sn of x minus Vt, you're going to the left, right?
Yeah.
So that term is reducing.
Yeah.
Because there was some entanglement, maybe I mean it's wrong, but it's like your x is becoming, the system is becoming smaller.
No, but that's also relative at t equal to 0.
Right. So at t equals 0, you pretend that your system was small.
Yeah. Yes.
So you've got smaller system now.
Yes.
So I thought that region Vt in your system was being replaced by this new equilibrium S. But then it's confusing me that E and V are not the same. At least I'm not. Do you understand? It's probably a very ill-stated question. I'm sorry.
So higher, I mean,
You're replacing it with something more entropy, right?
More entropy, that's fine, but should we have expected it to be sort of lower? That there's a front. What was there is being replaced by what is to follow. At least that's what I was thinking. That's wrong. So it seems like what's being replaced is moving at speed V, while what is replacing it is moving at speed E. That is confusing.
It's not speed, it's energy.
But the final entropy is E times S equilibrium times T.
Yeah.
So the distance is E times T. So, so that's why I'm thinking of E as a speed. But it's an entropy density times a length.
Mhm.
The length is grown linearly with time, so the coefficient of that you know called speed, right?
So, see how this return line where I'm looking at the entanglement across this cut. And then somehow you want to imagine that like in some region around this cut, I'm replacing the state with the
Yeah, with something else. That was my picture. Is that completely wrong?
I'm not sure that. Yeah, I'm not sure if that is the right picture for understanding these two terms in this formula.
Okay, it's probably wrong. I'm sorry.
I think what is true is that depending on the state, like so if I started with an initial product state, then at time t, I should imagine that the system looks like the equilibrium state sort of in this region of size 2 VET. And then this formula is telling me that if I started with some more general initial state.
Where VE there is E at 0, right?
Yeah, so it's like some up to some factor of
Epsilon.
yeah, epsilon 0 times S equilibrium.
Yeah, so that case was perfect.
I think when you start with the pure state, this interpretation somehow makes sense, but when you start with this equilibrium situation, it
Yeah, so somehow in the right. So now consider the case where it was already the equilibrium state, then nothing
Nothing
has to
happens.
happen.
But now say half. There was
Some-
less entropy here, more entropy here.
Yeah, then-
or the other way around.
Yeah, then the result of this
Let's-
formula, I don't know what the intuition for it is, but the result is telling me that now this region where it is becoming exactly like the equilibrium state is growing at a smaller rate. It was like 2 epsilon.
But smaller rate, but what's confusing, okay, whatever rate it's growing at, what's confusing is that replacement rate is different. That Sn x minus v. I'm so sorry.
Yeah, so sorry, I'm combining this into the rate of entropy growth.
I see. So I should just not think of these two terms to be separate.
Yeah, so.
Okay, yeah, sorry.
So the actual rate of entropy growth, let me just write down an explicit formula. Is something like minimum over V. Epsilon V times S equilibrium minus S times V.
Yeah.
So then this is giving me the weight of this front for different
Fine.
energies.
So at the end of this whole process, you get an effective velocity.
Yeah.
Okay, fine. You should think of that as replacement and this as.
Yeah, it might be useful to think about it that way, but right now I'm not.
But it doesn't sound right. So, yeah.
What is the SV? What is this?
So S was the, I was considering this general family of states with initial entropy S times volume of the region.
So this formula is sort of a intermediate time. It
Exactly.
doesn't work towards the end and it doesn't work right.
Yeah, exactly. So I'm not thinking about order 1 differences in time, order 1 differences in entropy.
So this T equal to 0, why is T equal to 0 special? That gives that.
Characterizing the initial confusion.
That's what was
Initial meaning some time stability.
How it started.
No, but that's how, I mean, this is T, right?
At t equals 0 at some other point in it.
I see.
You're looking at what?
So the statement is just like, because you expect that for different initial states, the entropy should grow at different rates. In particular, if you start with equilibrium state, it should not grow at all. So that should play a role as well. Like which initial state you start with should play some role in the one.
But let's say I cut it at some other point, this initial slice for me is somewhere in the middle. Then also it will work.
Yeah, good point. So in that case,
So it's highly consistent.
yeah, it will be consistent because this formula is ignoring order 1 changes in the entropy. Like sometimes T you would manage to build some entanglement across every region for some width, but I think you would not be able to change the overall volume law coefficient of the entropy in like a short amount of time. So this is not very precise, but the overall thing is that if you are taking the scaling limit, then it should be consistent whether you start at t equals 0.
So it is the fact that, this consistency that after evolution T, the entanglement that I obtain from some initial configuration at T equal to 0, I should be able to obtain it by first going to some T prime in the middle.
Yeah.
And then from T prime So then I figure that out what T prime is using this formula, and then from T prime I go to T, and then use that T prime is 0, and then T minus T prime to compute that, and whether these two are the same
Yeah.
is not very obvious from this.
It's not obvious from this, but it's true as a result of the fact that you're in this unit.
Isn't that like taking curves which are not straight? You're taking building curves also. And that would be like minimizing over all building curves. But she's saying that.
Yeah, good point.
straight lines.
Yeah, so, right, so you can consider sort of, what you're saying is like, if I break this minimization into 2 steps, right? So first I consider some intermediate time T prime, and then I consider all possible velocities with some other time from T prime to T to the 0. And so from this I would get a sum of 2 contributions. But you can, so if you want, I can show it more explicitly, but you can use, so this gives an overall contribution which looks like epsilon v1 t1 plus epsilon v2 t2. Where this is v1 v1, this is v2 t2. We call this t2. And then I want to compare this to a configuration where I just take a straight line. And then that would give me epsilon v1 plus v1 t1 and v2 over t1 plus v2 plus t1 plus v2. And then using convexity, this is always monotonous, or this is always monotonous.
That's this convexity.
Yeah. So actually, yeah, that is the reason why convexity should be important. Thank you for. Okay. Okay, so this was just reviewing the formula, and so this, from this whole discussion, we see that it's a pretty reasonable conjecture, and the evidence that has been provided for it so far is from random circuits, which I mentioned, also in holographic CFTs. As I mentioned, thermalization in the boundary corresponds to black hole formation above. So we can consider some geometry where a black hole is being formed from some collapsing matter. Calculate the entropy of some subregion as a function of time using the HRT formula. And then if you take a special scaling limit in the HRT formula where the characteristic size of the region and the time are both much bigger than beta, then in this limit, you can get rid of the radial direction in the bulk. You just end up getting a minimization problem with this one. Okay, again, with some non-trivial function epsilon, which is different from the one that you get for random circuits, but it satisfies the same constraints.
So your configuration hugs the horizon.
Yeah, it comes from that geometry.
Yeah.
Is about the setup where you consider your system to be finite.
Yeah.
We talked about entropy density. Density, that confuses me.
So what do you mean? So if there is, you mean the initial entropy density or the eventual entropy density?
Yeah, because it's not necessarily going with volume, or is it going with volume? Is that what the intuition is?
No, the growth is not with volumes. The growth is linear in time with some order 1 coefficient. The eventual value will be proportional to the volume.
I think the question is, what about finite size connections? Meaning, why can you talk about densities in a finite size system? And isn't the other sum
Is that what you're thinking? I think it's because I'm taking this particular scaling limit and I'm ignoring the finite size corrections.
It's a very big system compared to the intrinsic landscape.
I'm always in the thermodynamic limit, and I'm just looking at things which sort of scale with the overall size. So these calculations I mentioned for random circuits and holographic CFTs are sort of the 2 analytic derivations of this membrane formula.
And in the holographic formula, you get a derivation for this ENV function.
Yeah, you do. So it's some very simple function in the case without any conserved charges. Like it's just 1 over v squared minus 1 to some power, which depends on the dimension.
Sorry, in that again in the holographic setup, you could go from one temperature to another. Like you could have start with a brane, then have some thermalization to go to a higher temperature.
Oh.
And then this will play out in an interesting way, like we.
That should be interesting. Yeah, I don't know about that. It might have been like Mark Mazzei had one sort of earlier paper about the simplest cases. Then he had
Simplest case meaning 0 temperature to finite temperature.
no, where not I would not say 0 temperature, right? Because the initial state that you have is at the same temperature as the final state. But
energy content.
Okay.
yeah.
Sorry, I thought what was happening. Sorry, I misunderstood. I thought what's happening. Maybe it's wrong context, but I thought we start, let's say, in the vacuum, and then I throw some energy in, and then I try to compute how the entanglement entropy grows.
Yeah.
So the initial temperature from that way was 0 because.
Oh yeah, sure. But the actual temperature of the equilibrium state is determined by the energy after you've thrown in some energy.
Great.
So that is what determines this coefficient.
Yes.
So I don't know. It sounded like you were thinking of cases where you start with one
So
temperature.
start with a black brain at 1 temperature. That's the initial condition. Then I throw in more energy. Eventually, it'll become a black brain of another temperature.
Yeah. So then I expect the equilibrium entropy density, which appears as the final state.
Yeah.
And then this should select like
Some particular
the
class.
corresponding to the earlier temperature.
Like we were discussing before. Yeah.
Yeah, but it might be interesting to see that more explicitly.
Maybe you mentioned this, but do the CFT if one carries this out, because therefore you one can do these calculations explicitly technically and so on.
Yeah.
So there also one gets some sort of a function, universal function that depends on some charge.
Yeah, there's right, but in 2D CFT, it turns out if you do the calculation for holography, then somehow the case of 2D CFT is degenerate. So actually you just get a straight line, you just get some constants. So that has to do with somehow 2D CFT being very special. But I talked a little bit to Mark about this, and he said that if we deform the CFT with some perturbation, then you should get a more generic shape like this. Yeah, but like, so the answer even to holography is very simple in that case, and you can probably reproduce it directly with the CFT technical thing.
Sorry, and in the holographic setup, we've got a particular RT surface initially before we've thrown the energy in. Let's say it's hugging the original horizon.
Yeah.
Now we throw some more energy in.
Yeah.
And then the surface sort of relaxes to the correct one, I suppose. And it does it all over space in the same. So how roughly what happened?
Yeah, I don't know what happens in that case, like from the gravity side. The formula that you get is that it should grow, the entropy should still grow at a constant rate. So I guess, like in this particular scaling limit, it would always be hugging the horizon of the new black hole.
Right. So you've got this thing, and sort of like from the end, it starts rising.
Yeah.
Is that the picture? Okay.
Don't fully understand.
Meaning you had, let's say you had a surface which was at X, anchored at X on the boundary, and then going off to infinity.
Yeah.
So it went like this and then hugged the horizon, the initial horizon here.
Yeah.
And then now you've thrown in some more energy.
Yeah.
And is the picture that this surface now from here on starts readjusting with the front moving towards the left?
Right. So later in the geometry, you would have some horizon corresponding to the new black hole.
Horizon.
And somehow that should be the only relevant one for the.
But I was trying to understand how it reaches that.
Oh.
Is it like a front?
Oh,
of
that
that
I don't
surface?
know.
I mean, the new horizon has jumped out there.
Yeah. So it has to go up.
Starting surface has now gone inside.
Inside, so it has to
Then
come back.
Sort of hugs the horizon like that.
But so I was trying to understand the front velocity. So some part of it has gone back, has been pulled back up. The other part is still below.
Yes.
And it's moving with some front.
Yeah. I think it's sort of close to hugging the horizon.
But
Kind of like.
hugging the actual horizon.
Like the second one.
I see. So sort of speed of light.
Basic question, why are things hugging the horizon?
Oh, so this is this so-called, so this is a result of
This is Mark's
taking this particular limit. Yeah, so Mark has two papers. One was this one where he interpreted it in terms of membrane, but he had another one from 2016 where he basically showed once you take this limit, then irrespective of which specific geometry you have, like you can take the Hartmann-Maldacena setup, or you can take this Liu and Su setup where you have like a Vedia geometry where you have initial infalling matter which collapses to form a black hole. In both cases, the only thing that's relevant is like the geometry of the eventual black hole. And then the RT surface, there's some picture where.
Yeah, if we could draw some control patterns.
Yeah.
We check these two quantities if either.
So, okay, so on the boundary, I have this transverse direction.
Either. Okay.
I'm considering the RT surface for some region.
Okay.
So now let me project this out. So the artery surface will sort of start here, then it has some behavior like this, then it comes back to the point. So these are the two endpoints of A.
I see.
But for most times, it remains sort of hugging the horizon.
I see.
So then I think Shreya's question is like in a geometry where you have two horizons, then how does it
Okay.
change? Yeah. Okay, cool. Yeah, so the eventual conclusion I think is that it should just have mostly the second horizon.
Yeah.
So Mark's formula still has this form in three-dimensional geometries, right?
Yes, it has the same form, but you replace, like I was saying here, replace V with like absolute value. And then integrate this over the surface.
So one guess would be that if we did this calculation to these CFTs, but just pick the universal identity block,
Yeah,
perhaps we would reduce this.
yeah, I think you should be able to. It's just that you will not get a whole function, you just get a constant function. Yeah, again, that is a non-trivial calculation. I can just see that it's a constant.
Yeah, so I took also consider the reverse process to what Shreya was saying.
Okay,
That heat loss.
okay,
Suppose I have the hot system in the context of cold baths,
okay.
and then I could do a heat loss, which then takes you to some lower temperature system.
Okay,
So, which perhaps might correspond to black hole evaporation or something, but at least the statement context is clear. I have a hot system in context of the cold bath. Okay, these formulas are generally enough to describe that situation.
I expect, maybe not because that doesn't happen in generic systems, right? In generic, like you need to do something special to the dynamics to make the entropy decrease. So if you have some.
Saying put transparent boundary conditions at the boundary radius.
Yeah, I think so. Maybe in holography you can do an explicit calculation. Then we could check whether it takes this form or not. Maybe it still does. But I don't know if there is intuition just from like boundary chaotic systems for whether there should be a universal formula for that or whether it should depend on whatever details of the dynamics.
There are complicated models like Anderson and Millikan, Amiri, and so on, where they do have such systems which describe some kind of black hole evaporation.
Okay.
This one, yeah, we can discuss this.
Yeah, that would be interesting. But yeah, I think so. In any specific model, there might be some analog of this formula. But I don't know if we should expect a generic. Okay.
Sorry, just to say again, your formula is for closed system.
Yes, absolutely.
Whereas Gautam's formula would be coupling to a bath. Right? So it
Yeah, but then you could think of the bath and the.
as part of the bath.
Yeah,
Okay.
but even then, you never expect in a chaotic system that the entropy would ever decrease unless you're doing something very like something very special.
But once you include the entropy of the bath, things certainly cool down, right?
I just mean that if you have some small system coupled to a bath and you're looking at the evolution of the entropy as a function of time, you would never see it decreasing.
Well, if it's a hot system, it's coupled to a cold bath, it'll lose energy.
Oh, yeah, sure.
It's just that there's a lot of energy density in this, like some small part of the system.
I guess, yeah, I can imagine it would lose energy, but it still seems unintuitive to me that it would lose entropy.
No, it won't lose total entropy, right?
But the system will lose energy.
Yeah, but not the whole.
And it's below the entropy of stage.
Local point.
Yeah.
Energy and something.
Yeah. Okay, I'm not entirely sure. Maybe, yeah, maybe we can discuss it later. So the questions that I want to address in this talk is because the calculations that we used were very different in the different kinds of systems. Is there some way to see all of this coming from some common underlying structure? So the kinds of questions I want to answer are: what is the meaning of this function and its velocity dependence? Other than its consequences, what aspect of the system do we see it coming from? And so for hydrodynamics, we have an understanding of late time behavior of correlation functions in terms of some low energy gapless modes, which are universal across all chaotic systems. So can we give some understanding of entanglement dynamics and in particular the membrane formula in terms of some kind of low-lying modes? And if so, then what is their structure? Okay, so these questions are intentionally somewhat imprecise, but I'm going to discuss how in a particular class of models which have some random time-dependent Hamiltonians, we can give very precise answers to them. Okay, and then hopefully that structure also generalizes. So the thing that I want to emphasize even more than the specific calculations in these models is the structure of the result, which I think might be more generalizable. Okay, so in particular, we'll give some understanding of the membrane tension in terms of certain gapped low-lying modes, and they'll have some dispersion relation, and that dispersion relation will be related to this membrane tension function.
E of V, you're calling the membrane tension.
Yeah, exactly. And maybe I'll call it epsilon because E will be something else in the rest of the discussion.
So these are modes of the evolution Hamiltonian.
So I'll explain in a second what their modes are. They're not modes of the original. They're modes of some effective Hamiltonian which lives on multiple copies of the system. So maybe before we go into the details of the models, I think we have enough time to finish by 1 or so. Okay, so then let me provide a little bit of intuition for what these modes will look like. So you might remember this picture from when I gave my talk on the equilibrium approximation a year and a half ago or so, where the quantity we're interested in is the time evolution of the entropy entropy. So I can write this as trace of the A, trace A1. So this has n e to the minus iht in it and n e to the iht. And I can give some path integral representation for this quantity. So I can write it in terms of n forward going contours and n backward going contours. Okay, and the fields which live on this are labeled phi1 prime, and so on until phi n prime. And then the expression is you have some path integral. The initial conditions are determined by the actual initial state or 0. The final conditions are determined by how you're taking the traces in this quantity. We have some factor inside the path integral, which looks like sum of I 1 to n s by I minus s by I times. Okay. And last time I pointed out that you can notice a specific set of configurations here, where the fields on each forward-going contour are equal to the fields on some backward-going contour. So, and the number of ways you can do this is the number of permutations in Sn. So you can have some relation like this. So phi I is equal to phi prime sigma I. So this special set of configurations is somehow stationary, and if you have a chaotic system, then at late times, it's intuitive to expect that maybe everything else that's not associated with these permutations gives you a large number of fluctuating phases which cancel with each other. So somehow the intuition is that that gives you the equilibrium value of the entropy. And then we made this more precise with this equilibrium approximation.
So it's like a replicated Schwinger-Kelvin.
Yeah, exactly. This is like a Schwinger-Kelvin with n time folds.
But in the end, you basically end up with a picture which follows from randomness of the evolution Hamiltonian, or the evolution operator, right?
But we're not, like, at least in this reasoning, we're not explicitly using any randomness. The randomness is somehow coming from the fact that the Hamiltonian is chaotic. And then you would end up with a large number of phases, and there's no particular relation between the phases because it's chaotic. So in that sense, we're using randomness.
No, I'm saying even if you just consider like page type problem, where you have some this is the system with n copies, and you take random operator of each and then average, then you get some index contractions which are basically some more permutation elements, just like that, right?
Exactly. So that is.
So the mathematically it's basically following the same structure.
Yeah, it's following exactly the same structure.
And your motivation is also the same, right? That you're using chaotic nature of the Hamiltonian.
Yeah.
And so on. or maybe you have some other argument to, to argue that these types of boundary conditions are what will dominate the path.
The argument, the motivation for it is exactly coming from calculations of Haran and unitaries, which select these permutations.
Fine.
And then the idea is that this is some motivation for why it might apply more generally. Even in cases where you don't have any randomness in the time evolution.
So what is that argument for the latter part?
So the argument is a sort of vague one where you say that these configurations, this is the correct expression for the path integral for any system. Then you notice that these particular configurations, the phase cancels. So they're special in that sense. And then in all the other configurations, the phases are not canceling. So at late enough times, you're getting the sum of a large number of fluctuating phases. Okay, so this was for, and yeah, so last time I discussed how to use this idea to get, so this idea I should say is from a paper by Nathan and Zhou, which had a lot of insight on how to think about these systems. And then we can also consider that if we want to consider late times, but not quite at the saturation time, okay, then a natural thing to expect is that we have configurations which locally look like this. So we have some spatially extended system. And say that in different regions, locally the configurations look like this, but maybe you have different permutations in different regions. So then the phases are cancelling everywhere except at the boundaries of these regions, but that's those contributions should survive for a much longer time than contributions where the phases are fluctuating everywhere. Okay, so that is kind of the intuition for what I'll discuss in the rest of the talk. So these permutations will still play an important role. Okay.
So this is not the boundary which is separating the system for the system from the environment, but some dynamical boundary.
Yeah, this should be considered just any boundary.
Any surface, okay.
Yeah, roughly both like this, and if you have fewer boundaries or shorter boundaries, then those should be better than having longer boundaries. Yeah.
So you should think of system. I mean, all these things happening in the system.
Yeah, this is all happening on n copies of the system in some effective dynamics.
No, I mean system meaning just A, not A bar.
Oh, no.
Where is A and A bar in this picture?
They could be anywhere. So the A and A bar just enter as boundary conditions. But what I want to say is that in this path integral, irrespective of the boundary conditions, the kinds of configurations which should dominate are ones where locally you have either one permutation or the other. And then we will see in the rest of the discussion how having A bar at a particular location fixes. Well, intuitively, if you have, like this boundary condition has a particular permutation, eta in the region A, which is this. Actually, I have not said this, so let me introduce the notation for that. But basically, you have these boundary conditions from trace A and trace A bar in this quantity are setting particular permutations in this region and this region. Now, if this is A and its complement is A bar, then those boundary conditions can sort of propagate into the bulk of this pattern.
Yeah.
So sorry, this is a notational point. So phi one, you want to split into a double line, is it like phi one A,
Yeah.
phi one A bar?
Sure.
And then join up the A's pairwise and then whole of A bar later. That kind of stuff, right?
Yeah, so you always do that at the boundary because of the boundary conditions.
Yeah.
To get the equilibrium value, you have the same permutation in both A and A bar in the bulk of the path integral. But now, if you want to find the approach to equilibrium, then you should also split them in the bulk of the path integral.
And that's where you introduce the different
Exactly. Yeah. The specific class of models I want to consider are so-called Brownian models. So in this talk, I'll be discussing the case of one spatial dimension. So imagine that we have some lattice like this. And we have some time-dependent Hamiltonian. So it's a sum of local terms. Okay, and each of these H alphas lives on a small number of local degrees of freedom. Okay, and I'll consider two kinds of choices. So one is that you can take H alpha itself to be a random matrix. So that would be essentially forget all the internal structure of these degrees of freedom and take H alpha to be a random matrix. Or you can fix some particular operators P alpha. And then just take the coefficients that appear next to these to be random. Okay, so then in that case, H alpha is like J alpha T times P alpha. And this J alpha is some real number, which is random, and B alpha is some fixed operator. So the advantage of doing this case where you just take a random matrix is that the calculation is much simpler, but we want to be able to comment on the emergence of universality even in more specific chaotic systems. So that is why I want to emphasize also this choice. Okay, so in both cases, we'll take the time-dependent Hamiltonian at different times to be uncorrelated and also uncorrelated for different alphas. Okay, so let me write down what that means specifically for this case. So we'll take the averages of these numbers J alpha T be 0 and J alpha T will be the average, let's see, given by this. So this delta alpha beta is telling me that the different alphas are uncorrelated with each other. G alpha is just some number which is determining the strength of this coupling. And this delta T prime over, so I'm discretizing my time in steps of size epsilon, which I'll eventually take to 0. And this should be seen as some discretization of the delta function between T and T prime. Okay.
Are there a large number of degrees of freedom in
So no. Yeah, we are not, well, sorry, there's a large system size, but at individual sites, I'm not taking, I will at some point take a limit of large Hilbert space dimension in a particular case, but then I'll more general case.
more generally?
Okay. And it's crucial to that the randomness is in time as well, not just in space.
Yeah, so that is a sort of unrealistic feature of this model. Like eventually we want to describe just cases where you don't have randomness in the time, like all times have the same Hamiltonian. But this turns out to be something which simplifies our calculations a lot. So and previously such models have been used to give a, like if you don't look at entanglement entropes, but just look at 2-point functions and take a version of this model which conserves some U1 symmetry. Then you can give a very sort of simple and nice derivation of diffusion. So this was discussed in a paper by Galia and Mokminich from last year. So and diffusion is okay in this particular model. You can see the diffusive modes coming out in a very simple way, but diffusion is something you expect to see in any chaotic system. So the same logic should apply here. But maybe the lessons that we learn from these models are more general.
Okay, I guess I was wondering, the case where you take your H alpha to be just a random matrix living on sites.
Yeah.
How is this different from the random unitary gates applied to unit sites?
So it's physically very similar. I'll mention some concrete differences that come up. In some sense, it's because this evolution is continuous in time.
Okay, so that's of course different, yes.
That's different, and it also has some physical consequences. Okay, so good. And then the time evolution operator is just given by a product of things like this. So we have time steps from 1 to T over epsilon. Even known as IH Y. Okay. So the key simplification of these models is that you can rewrite the Lorentzian evolution on 2n copies of the system as some Euclidean evolution on 2n copies of the system, somehow by making use of these random averages. Okay, so that is sort of the key insight which will let us make progress in this set of models.
So can I say it again?
I'll write it down. So sorry, I should say it again. So the Lorentzian evolution on 2n copies, like in this 2n contour Schwinger-Keldysh contour that I was describing, can be replaced with a Euclidean Hamiltonian. And so then this having a Euclidean evolution is very nice because then at late times you just need to understand its low energy properties. So you can use a lot of intuition as well as techniques from low energy physics to understand equilibration.
So this is not the same as H of Ti.
No, not at all. So I'll explain what this Euclidean Hamiltonian is. So before that, let me write down an expression for the nth Renyi entropy as a transition amplitude. So this will also look familiar to those of you who were there in my previous talk. So we want to find this out now. And this can be written as a transition amplitude of the following form. So I have to define what all these states mean. So everything here lives on 2n copies of the system. And I've defined some states O sigma associated with some permutation sigma in Sn. And O is an operator on one copy of the Hilbert space. So this is given by O one I prime sigma one O I n I prime sigma n. So product of all of these things. Okay, so this is just a kinematical rewriting in any system of the nth Renyi entropy as this transition amplitude. And this eta, so E refers to the identity permutation, which sends every element to itself. And eta is the cyclic permutation, which sends n to n minus 1, n minus 1 to n minus 2, and so on. Okay, so in this expression, the simplification in these models will be that I can replace mu times u star to the power n after averaging with some e to the minus p to n t, where p to n is the Euclidean Hamiltonian, which lives on 2n copies. And the explicit expression for it is it's given, so for this case, it's given in terms of these different d alpha operators. As this form. So I should explain what this notation means. So I'm labeling, I had n forward copies, so I call them F1, F2, and so on up to Fn. And then I have n backward copies, and I'm calling them V1 to Vn. So you can see that there's a symmetric structure between all forward copies and all backward copies. And sorry, I'm missing the square. Okay, so it's some Euclidean Hamiltonian with a sum of non-negative terms. Okay.
So, this structure is well known how it emerges out of the Brownian circuit. This structure is definitely absent when you do ensemble averaging with some noise that is time independent. Is
Right.
this structure going to be important for your results?
Yeah, so I'm talking in the context of different systems, but I somehow want to identify modes which I think might somehow be present more generally. But this is absolutely the
It's very unique to this delta. Seems like a
yeah. But the thing that we're going to be able to tune microscopically even within cell deltas is just all possible choices of these couplings. And then yeah, so we'll probe robustness under different choices of these operators. Okay. Yes.
And then there are some boundary conditions also.
Yeah.
Since you have doubled the units, where are the boundary conditions?
So the boundary conditions were in the expression. Yeah, so this is just so this is just a property of this time evolution. And then the boundary conditions are present in the expression of the entropy. So. Right, so I have this final boundary condition, which puts the eta permutation in the region A and the identity permutation in the region A bar.
So did you say why it's the cyclic one?
No, I didn't say why. So one, so that is somehow just by manipulating these indices. Yeah, and it has to do with the fact that we're calculating trace of A, trace A bar.
Right.
So you're taking the traces in a different way in A and A bar, and that gives you this. Okay.
What was the G alpha?
The G alpha was the strength of the coupling.
What is FI and GI?
Oh, FI was labeling all the forward copies. So F1, F2, and so on, and then the other backward copies.
Sorry, but what is this subscript D alpha FI? Alpha is a subscript for a
Which
pair,
kind
right?
of?
Yeah, by this I mean that I take
Oh,
the alpha on FI and identity operator on the other copies.
So, but a FI that you mean a pair.
No,
It's a two bilocal operator, right?
no.
D alpha?
No, it's a single operator which lives on just the FI.
Oh.
Yeah.
What is the meaning of this blob covering two dots?
Oh, okay, there are many different indices. So this is, yeah, so I should say I consider the n equal to 1 case, so I have two copies of the system. So then this is F1, and I should have a second copy F2. And then this B alpha F1 lives here, and B alpha F2 lives here.
And it's
Sorry, B
summed
alpha
over,
B1 lives here.
it's summed over all the pairs.
Yeah.
Where is that sum?
So I'm allowing something more general because I want to consider cases where, say I have multiple operators corresponding to each side. But yeah, as for instance, I could take.
Oh, that's the final alpha sum, I guess. Yeah. Okay.
Yeah.
Fine.
Is P alpha a positive definite?
Yes.
Yes, because it's the sum of positive definite operators.
And sorry, what broke?
No, P alpha.
It's like not P2N, yeah.
Yeah, not the alpha.
P2N.
G's are positive, right?
Yes, yeah, because they are variances.
Why did the evolution become positive in forward time as opposed to backward time? Where did that happen?
This has both forward and backward times in it, or.
I thought that you're effectively moving from in time in this Euclidean problem. Maybe I misunderstood. But somehow if you can't then effectively move back, right? If this is positive. Sorry, maybe it's very stupid.
Yeah, that's true.
Where did that breaking of time reversal happen?
Somehow because of this randomness.
Random average.
Random averaging change distinguishes T from minus T.
Time, yes, random average time. It's very specific. Markov semi-group.
But I thought it was time by time. So how does that distinguish plus T from minus T?
So if you calculate something which was evolving backwards, you'll also get the same Hamiltonian. It's still positive definite with time.
Okay, so then I'm not understanding. Sorry.
Yeah, I think what he's saying is that because you get some Hermitian operator e to the minus P2 and P, then you can replace the forward and backward conditions. You get the same answer.
No, I mean, if P is positive, then the time direction of Euclidean time is chosen, right?
And it's chosen because
The thing that decays.
yeah, if it were the other side, it would have blown up. It would have blown up this side, right? And you're calculating something that's bounded, so it can't possibly blow up.
Yeah.
That's why that sign is chosen.
Yeah, but how is it?
How did it break the symmetry?
How is it chosen? From that average and everything looking fine here, symmetry between T and minus T.
It's an open quantum system.
Sorry,
It's an open quantum system.
open quantum, but where did
It's
you?
not an open system, right? It's random.
It's effectively, because noise is timing.
No, but still T going to minus T, everything is symmetric, right?
This is something.
You mean just at the level of the equations and.
Yes.
But suppose I wanted to go back.
Because it's the mathematical formula, right? The one that's underlined there, right? That's a mathematical thing.
Yeah, so Neva, you're saying that physically, this can be thought of as.
Interpreting them as an effective Euclidean.
There's a lot of
But why can't I
the information on the tonic you get in the loss of the environment. Systematic. And this Brownian
But it's not, the information is not getting lost in the sense that the evolution, like, the time evolution is still a unitary operator.
your average. You're averaging over unitaries.
Yeah,
That's not a unitary.
so, but we're averaging the final quantity over the unitary, we're not first averaging the unitary and then time evolving. So we do this all the time in calculations of, chaotic systems.
Yeah.
They started from the dagger.
I shouldn't think of this as
They-
a.
If you started on the dagger, you would have gotten the same.
Yeah.
Then.
Yes,
Yeah.
yeah, okay, that's a good way of thinking about
Right,
it.
because we could repeat.
So even,
No, I'm just saying if you started not with you, but with you dagger.
Yeah.
You probably would have gotten the same.
you get the same thing.
Yes.
Yeah.
Absolutely.
Yeah. What is still confusing me, I'm so sorry, is that I'm thinking of this as like, but Onkar was explaining, I'm thinking wrong, but let me just say it. I'm thinking of this as like some effective time slicing of this whole system, including two entropies, right? And then you're telling me that somehow you're saying there's a mod T, which I don't understand. Mod T, right? I mean, you're saying going backwards and forwards are not inverses of each other.
So wait, so this e to the minus p20 is the bar is on the left is up on everything, right?
Yes, yes.
On top.
Yeah.
That's why it doesn't matter.
That's why I was- I'm probably being very stupid. I was just thinking that you're inventing an effective Euclidean problem that is taking you from here to there, then taking you backwards. Why isn't that the inverse of this?
But you've done going forward and backward both and then average. All the trajectories are with the forward.
I suppose so.
Because the forward and the backwards and then you average.
Yeah. Okay. But you're still thinking of this as a transition amplitude, right? Between here and here.
Well, yes, I think this point is useful that, right, so every quantity can be written that we're interested in can be written in terms of some U and some U's and some U daggers, then reversing time is like replacing U with U dagger and vice versa, and this whole structure is left invariant under that.
Okay,
But the right hand side is not, right? E to the minus P and T, if T goes to minus T, you get E to P and P. That's the question.
It's absolute value of theta.
Yeah, but where is the absolute value coming from?
I mean, it couldn't have been anything else.
Yeah, it is, yeah.
Like if you thought that it was, and you could have guessed that the sign there is wrong, but it couldn't have been because
No, but T equal to 0 is special in that it's the maximum and then everything is decaying from that side. But where is that T equal to 0 choice? Where is that T? Because you have this kind of picture now.
Yeah.
So this is clearly special.
But it's not that.
I'm not sure at a formal mathematical level, but at a physical level, somehow this has to be the case of you.
Yeah, it's clear that it's clear. Yeah, physically it's clear. Right.
Yeah. Do you have a remaining objection?
I'm just saying it's explicitly non-unitary evolution. I don't know why it's.
It's not a unit, it is a.
So take a particular realization of GFT, right? You evolve with that, right? And then you pick another realization of that, you sum these evolutions. It's not unitary evolution.
We're not, but I think what you're saying would be true if I was doing the average like this.
No. Any form of averaging in this context.
So for any particular choice that I take of the h of t, for some fixed values of j alphas, the evolution is unitary. Then I consider many such, then for that evolution, I compute the evolution of the entropy. Then I consider a different realization, then I compute the average of the entropy. So then I compute the entropy, then I average over all of these things. That is averaging over a large number of unitary processes, not considering.
Which is not effectively reproduced by a single unitary.
That's fine, that's
clear.
fine. That's fine.
Yeah, but the idea is that it gives you a sense of what happens in the typical case of these things.
Sure.
Yeah.
Sure.
So. Okay, Okay, so now our goal for the rest of the talk is, now that we have a description in terms of the Euclidean evolution, to try to, so since we don't have a lot of time left, should I try to derive this? Would that be helpful, or does that seem?
It's completely up to you.
Okay, let me very briefly give some sense of how to derive it. So as I mentioned, you had a product of these e to the IHT and e to the minus IHT for different epsilons. Let me just do the n equal to 1 case where I have one forward and one backward copy. So I'm considering e to the minus I HFT epsilon. Okay, so the idea is epsilon is small, so let me expand this for some small time intervals. So 1 minus I 16 epsilon minus small. So and then I have tensor product with a similar thing on the other copy. Okay, so now the idea is that we first look at the linear and epsilon terms. Those will all vanish because of this average over single J alphas. Okay, then we can collect all the quadratic in epsilon terms, and then that gives us. Then we'll find some things which survive because of these averages, and that can be collected into this form. And in particular, so we get an epsilon squared from this expression, but then there is a 1 over epsilon here because of the regularization of the delta function. So eventually you end up with 1 minus P2 times epsilon, and then you can re-exponentiate that to get this expression. Okay.
Yeah, somehow related to that issue, right? That the linear term in epsilon cancel, even epsilon square.
Yeah.
So that's like even in time.
Yeah.
What has happened I think after that? I mean, for higher orders, it's not.
We're ignoring higher orders because of
Gaussian bias.
because we're assuming epsilon is small. So we don't need to keep order epsilon. And then then you get some positive thing from collecting these.
But finally, you want to exponentiate it up, right? The minus P and T.
Yeah, so you get e to the minus, and for that you want this to be linear in epsilon, which it is because you had an epsilon squared times 1 over epsilon.
So the meaning of e to the minus P and T is just 1 minus P and T? I mean, this is only valid for small t, is it?
No, so I have 1 minus P2 epsilon for any small time interval. Then I can just combine, so this is approximately e to the minus P2 epsilon. Then I multiply this by T over epsilon when I combine them into this. Just using this product.
Sorry, Shreya, about the question I was asking about forward today, that I feel that going back in time, doing it the other way, is instead of taking inverse, as I was incorrectly thinking, taking dagger of that operator.
Yeah.
And since that operator is real, it just stays what it is.
Good. Yeah.
I feel
That's consistent. Consistent that we start with the dagger.
Yeah. It's just that I wouldn't use the word Euclidean time evolution because it makes you think of going up and down. Just some matrix element of some operator is how I would think.
Okay.
I mean, it's just words, it doesn't.
Yeah. I guess every physical quantity that you compute will be decaying, not increasing.
Yeah.
So, but I still don't understand how from here you get to this some finite time. That expression is to be valid for finite time or some very small time?
No, it's, so this was for a single time step here. So I can think of this as a product from I equal to 1 to epsilon, u epsilon times u epsilon star.
Okay.
Then for this, I found the expression for each, 1 to T over epsilon. So now I found that this by itself is equal to 1 minus P2 of epsilon. So then for that small time step, it's valid to do this. Right, then I put that back into this product. So for each small time step, I get this. Then by taking the product, I get epsilon times Q over epsilon.
That's why it's confusing.
I think it's related to that issue there because I mean, that's how you're getting, so the, yeah. Okay, maybe I'll ask you.
Okay.
Sorry. We need to this time numbers. You had your boundary condition set with the identity, identity on one side.
Yeah.
Do we have to change that?
Yeah, actually you don't. So if you change that, you end up getting the same answer because it's some real number and exchanging the forward and backward is complex conjugation. But what you should do if you're considering time dilation in the opposite direction, you should replace u with u dagger in both of these. But then the average gives you the same thing.
Replace u dagger and these and.
Then I think if you replace u with u dagger, yeah, probably. Yeah. Yeah, but it doesn't end up making a difference no matter what you do. Okay, so now we want to understand the late time evolution, we need to understand the saturation value, we need to understand the structure of the ground states. And then to understand the low energy excitations, to understand the approach to the equilibrium value, we need to understand the
one is not a hard limit. No.
Okay. Okay.
I mean, when you get really hungry, that's the
Okay. Okay, so good. So then let's first just very briefly discuss the saturation value because this is something that we've talked about a lot. So in this particular context, so e to the minus t2n as in the limit where t goes to infinity, just becomes the projector onto the ground state subspace of e2n. So all we need to do is figure out the structure of the ground states. And this turns out to be very easy to derive in general, just from the structure of, just by looking at which set of operators commutes with each of the b alphas on one copy. Okay, so in particular for the case of n equal to 1, so you have P2, then that is given by alpha, G alpha, B alpha F, means B alpha B. So this, it's a sum of non-negative operators. If you want to find a zero energy eigenstate, then each of these individually should annihilate the ground state. That means that B alpha F minus B alpha B transpose acting on ground state should be equal to 0. Okay, so this is a state which lives on two copies. We can associate it with an operator which lives on one copy by making this identification. And then just by manipulating these indices, you can see that this condition translates to the condition that this operator commutes with the alpha. Okay, so this is telling me that somehow the ground states are determined by the symmetries of my time evolution, which is very intuitive because that should be the only information of the time evolution that we care about for equilibration. Okay, so if we consider in particular the case where the system has no symmetries, then there is just one thing which commutes with all of these B alphas. So a couple of examples of that would be if I taken the B alphas to be, or if I taken these H alpha of T to be some random GUE matrices which live on adjacent sites and are time dependent. Okay, so that would be kind of the simplest example to do calculations with. Or I could make some particular choice of these B alphas to be like the couplings in the mixed field Ising model. So I could take them to be Xi, Zi, Zi plus 1. Okay. So these again don't commute, all of them will not commute with anything except the identity operator. Okay, so in all of these cases, for P2, the only zero energy eigenstate will be the state associated with the identity operator, which is the maximally entangled state between the forward and backward properties. Okay. And yeah, and then a generalization of this to the case where you have a U1 symmetry, turns out to give you like a larger subspace of ground states, which.
Charge, labeled by
Yeah,
charge.
exactly. Good. So now if you consider P2N, then because of the symmetric structure between like replacing different forward and backward evolutions, it turns out that in this case with no symmetries, you'll get exactly n factorial permutations, which are exactly these sigma states, for sigma s n. Okay, so then plugging in this projector into that transition amplitude expression just gives you exactly a derivation of the equilibrium approximation. And you can do it for the for the infinite temperature case or finite temperature cases, you generically get a derivation of the equilibrium approximation. Okay.
So somehow this problem of equilibration has become a problem of kind of ground state.
Yeah, exactly.
It's very weird.
Very weird, but very nice. Like, it's fun.
That's what happens in proper mechanics.
Yeah.
Yeah, exactly.
You've got dissipative dynamics, relaxes to the relaxes to the equilibrium. Hydrodynamics.
Yeah. So now we want to understand the structure of the low energy eigenstates. And in particular, the low energy eigenstates, which are relevant for the evolution of this quantity, which would be entropy. So it had boundary conditions like
Where is the maximum? Where is the fact that maximally entangled coming from?
just from interpretation of this operator, like this definition, it tells me that I get delta ij between the two states. So good. So now if I want to understand the evolution of Renyi entropy, then the boundary condition is eta and a cancelled with identity in a dot. And so I want to find some set of eigenstates which are relevant for this. Okay, and in the rest of the talk, I'm going to propose that the eigenstates generically, which are relevant for the evolution of this quantity, will have this structure. So they will be given by some plane waves.
It's the eigenstates of P2N.
Yeah. So these are low energy excitations of P2N above the ground state.
This is for the approach to the equilibrium.
Yeah.
So understand that.
Yeah, exactly. So these are given by eta permutation up to some site. Then for some order one region, you can have anything. So I'll explain that more. And then identity permutation after that site. Okay. So what does this mean? So I guess one thing to note is that sigma can always be written in a lattice system as a product of sigmas over all sides. Okay. So now I'm kind of generalizing that to have a single permutation up to some site. So locally this looks like the ground state, so it should not have a very high energy. Then this looks like some other ground state, and then in the middle you can have some arbitrary state. Okay, so these four permutation states, this could be some general state which lives in the Hilbert space of 2n copies of delta sites. Okay.
What determines delta?
Delta, the statement is that this is a good approximation for delta of order 1 in the thermodynamic zone. So the fact that there's some order 1 delta tells you that in terms of the entropy, it will imply that in the scaling limit of large sizes and times, you don't care about delta.
So the statement is this is a low-lying eigenstate if delta is small.
Yeah,
Some
this
choice
is a
of
good
phi.
approximation of the low-lying eigenstate for delta.
And you have to find the choice of phi that has it, or
Yeah, phi will be something arbitrary, which depends on details of the system. But the universal structure is this.
In fact, that eigenvalues are kind of imaginary energy type eigenvalues is the fact that it decays.
No, no, because because we want the eigenvalues to be real.
Right, I mean, in the OP, right?
Yeah.
Yeah.
Yeah, good. So this will have some dispersion relation in K. And this dispersion relation, so far this looks a little bit like hydrodynamics in the sense that we have some low-lying modes and so on. But this E of K, which will be the dispersion relation associated with this, will be gapped, unlike in the case of hydrodynamics. And E of K will turn out to determine this function epsilon. So you can think of epsilon B as a proxy for some dispersion relation of an effective Hamiltonian. Okay, so I'll establish a structure in a series of steps because there are many different choices I can make. But let me start with the yeah. So let me start with the simplest case where I take n equal to 2. And I take this GUE model where I'm taking random matrices drawn for adjacent sides.
Question? Is there a question? Somebody's unmoved it.
Okay, thank you. Okay. So the simplification of making this particular choice of completely random Hamiltonians is that in that case, if I consider all possible permutations of these etas and e's at different sides, like I take some general state like eta, and then eta, then whatever I get from acting with P4, so because I'm considering n is a 2, I now consider P4. I will also end up with some configuration of these etas and e's. So I don't go outside of the permutation subspace for this special choice. So, okay, so now I want to find the low energy eigenstates. So let me see what happens if I consider the evolution of the domain wall state, which is made up of etas and then e. So if I act with P4 on Px, then yeah, so essentially I need to find P4 that I get from this average. The result is that I get dx minus 1 over 3 times dx minus 1 plus dx plus 1. And then there is actually also another contribution.
Shreya, I'm really sorry at this stage, but could you just tell us eta and e what they are?
Yeah, that's very important. So eta is n minus 1 P1, which for this case is just a swap. And E is the identity limitation.
Eta is reversing order, yes.
Yeah, yes.
Okay.
And
eta acts on B's to give B's and F's to give F's on. I mean, your permutation acts separately on forwards and backwards.
Not cyclic.
no, so
No, I mean in the forward.
No,
Not
but
quite.
eta is a cyclic permutation
yeah.
in this case as well.
It's
like n going to n minus 1, n minus 1, that way.
Oh, I see. So that's it's that. Okay, and it acts on. So there were. Maybe I'm sorry if I misunderstood, but there were n lines for the forward motion and n lines for the backward motion.
Yeah.
And which is this acting on?
So this is defining a state which lives on 2 entropies. So
Yes.
let me do the n equal to 3 fields. So I have F1, P1, P2, F3, P3. So E, the state E, which lives on 6 copies, corresponds to this configuration.
Yeah.
And the state eta corresponds to this configuration.
Thank you. Now I get it. Thank you.
And you're going to choose whether it's E or eta each side separately.
In principle, I can. So I get some effective spin half Hamiltonian, which involves eta and E
Right.
on each side. In this case. Okay, so if I look at what that spin half Hamiltonian does to this domain,
Sorry, eta acts on full the set of all n sides, right?
so
what
it
do you
acts.
What do you mean you can pick it to be acting on one side?
I'm considering a version of eta for a single site, but 2 n copies of that site. So again, I have these 2 n chains. And then I'm considering, yeah, but now I'm effectively reducing that to a single chain.
Sorry, that was already the replica index, right? To F1, F2, B1,
Yeah,
B2.
so this is n. Sorry.
Sorry, that is now different from that 1, 2, 3.
Once you've
No, this is the same. This is the 1, 2, 3 direction.
Okay.
And this is the spatial direction.
Oh, that's the space. So when you say every site meaning that is space site, okay, fine.
Yeah. Yeah.
Okay. So when you write this kind of thing, you
That's
spatial, yeah, okay, fine.
Yeah.
Sorry.
But now, in this particular case, for the second Renyi entropy in this particular model, I can sort of compress this whole thing to be a single spin half system for each side.
Yeah, got it.
So then I see what that does to a state, domain wall state like this. And I can see that it has this action. So it keeps the domain wall in the same place, or it shifts it to the left, or it shifts it to the right. Or you can also have an order 1 over q squared term, which actually splits the single domain wall into different ones. Q is the on-site Hilbert space dimension. Yeah, I didn't define that. So
This is why large Q is easier. Yeah.
So yeah, large Q is easier because in that case I just have that. So and so I think you had also asked about the difference between this system and random circuits. So in random circuits, you only have motion of a single domain wall to the left or right without any splitting. In this case, you have some splitting of the domain walls. And I won't go into it now, but in the paper we have an interpretation of that in terms of operator growth. Like it's somehow the operator growth is more sensitive to whether the operator at a given site is the identity operator or some other operator. And somehow that's because of this evolution being more gradual. But okay, so now to understand the simplest case, let's first take the Q going to infinity limit. Then it's very easy to diagonalize this. And by diagonalizing it, you get exactly these plane wave eigenstates. So you get this. This is a left eigenstate of everything. It's a little bit tricky because I don't want to go too much into it because it's a sort of technical point, but if you get rid of the term which does this, then you get a non-Hermitian Hamiltonian at leading order, so then you can talk about its left eigenstates. But anyway, so the eigenstates have this structure.
Okay, very stupid question too. So this phi is spread over some sites.
Yeah.
Now, why doesn't your Hamiltonian tend to spread that out? Why does it stay spread over only those sites?
Intuitively?
Yes.
It's for the reason that I was mentioning earlier, that somehow configurations where you don't have permutations should be more suppressed. Sorry, so configurations where the different copies are not related by permutations should have more wildly oscillating phases and so on, so they should be more suppressed. Mathematically, in this case, it's because they have, like the ground states look like these permutation states. The other states have higher energy.
Right, so these higher energy things, they don't want to spread out a little bit?
They don't want to spread out much because then you're increasing the energy of the
I see, it's confined.
Yeah.
I see. Thank you.
Okay, so yeah, but at this level, like in this calculation, you just directly, you don't even have to worry about the phi's, you just get this answer. But now we want to understand sort of how, to what extent this result remains robust. Like, so we'll do that in a series of steps. First, we'll look at finite Q in this model. Then we'll consider this more general model with the fixed couplings that I mentioned earlier.
Sorry, and now the reverse question, why doesn't it want to shrink?
It does want to shrink.
It does, okay.
Yeah.
Sorry.
So that's exactly why you end up getting an order 1 delta. But it can't shrink quite to 0 because you have some non-universal things for short times.
So it eventually shrinks, but it takes time.
Right. If you take a scaling limit, then you never have to worry about these order 1 things. Okay. Good. So you can diagonalize this, you get this dispersion relation, you get this form, and you get some dispersion relation. It's also easy to write down. So you get 1 minus 2 over q%. So it has some shape like this, and it has a gap. Okay, so so then what will happen more generally is that
So what's the gap? 1 less.
it's 1 minus 2 over q. So in the q equal to 2 case, the gap vanishes, but then this is also a very bad approximation. So we now want to, so let's now, what will happen more generally is that these eigenstates will get modified to these more general eigenstates, but we will not end up caring about what happens in this region of size delta. It won't affect any of the calculations. but then this dispersion relation will change because of the effect of such terms, which will cause the memory, these domain walls to split and recombine. And that will have an important effect. Just basically, that is the important conclusion. Okay, so let me quickly show how when you plug this into the expression for the entropy, then you end up getting exactly the membrane formula. So, so the expression for the entropy had dx e to the minus p4p rho 0d. And then we said that dx, so we look at the backward evolution of dx, and it can evolve to domain walls at different locations under this large Q thing, but it cannot split into multiple domain walls. So you can write this, we can insert some resolution of the identity here. Just we get sum over y. And now this can be identified as the initial entropy of the region to the left of y. Okay, this is just again by the same definitions that I wrote down earlier. This is e to the minus sp x y of t. Okay, and this contribution is like some propagator for the domain wall to go from x to y. Okay. And now we can write it in terms of these eigenstates and eigenvalues. Because the psi k's were just plane waves of these dx's, you eventually get this expression. This is equal to sum over 2 e to the minus I minus and then, okay, now x minus y can be defined to be vt. And we can always replace the sum over 2 with an integral because we're in the finite limit. And then we can, because we're interested in the Lagrange limit, we can use some saddle point in this integral. And then the result we get is exactly of the membrane form. So we get e to the minus epsilon v times S equilibrium T. So in these systems, S equilibrium should always be just log Q because it's infinite temperature. And okay, and then you can write epsilon V as some explicit things. KB is the solution to so all I've done is just find the saddle point equation for this integral, which is this. Then I get some value of k for each v, then I plug back into this. So I get some function epsilon of v. Okay, so and the main idea is that that will sort of also continue to be the case in more general systems, but with the dispersion relation replaced with the actual dispersion relation for that system, which we'll find through some other techniques. Okay, and then another thing you can do to give an even more.
So sorry. On the left, we have this eta business, right?
Yeah.
And on the right, we have this E business. Did they have different entanglement entropy densities, the left and the right equilibrium?
No, so the entanglement entropy density can be spoken of in relation to this initial state.
Okay.
But eta and E are kind of the things which are calculating the entanglement. Like they're.
I was trying to make contact with the picture where there was an initial entanglement and then the final entanglement at the beginning.
Yeah.
Can I see that somehow here?
Yeah, but not from. So this is just the boundary condition which computes the entropy, right?
Okay.
So for eta and E, that doesn't make sense. But then here, this is where we were getting the initial entropy contribution.
But roughly, you can say that eta corresponds. I mean, if you replace an eta with an E, that corresponds to taking that site and putting it inside A. Right? Like taking it from A and putting it into A.
That's true.
So it's.
But I think what Shiraz is asking about is like what is the interplay of this with different initial entropy densities?
Yeah, this is like a domain wall between two different things. This.
Yeah, but
this
the
stuff.
domain wall is just coming from a kinematical thing.
Okay, so it's not to be identified with, like, fine.
No. So the domain wall is calculating the entropy of the region to the left of X.
Right.
So you remember this general expression? So the fact that this state turns into a domain wall state is just consequence of the fact that I'm calculating the entropy to the left of this.
Okay.
But then the initial entropy contribution is coming from this factor, which is just e to minus s to y and t.
Okay.
So now when I combine this factor with this one, and I sum over all y's, which is like summing over all these, then I end up with the minimization from the domain wall.
Shreya, if I take this picture, cut it somewhere.
Yeah.
And I see that line intersecting that time slice at some point.
Here.
Yeah.
Mhm.
Now that the line intersects there.
Mhm.
So what is the significance of that point? I mean, what will I say about that? So at that time, what is that telling me? Is there a way to say what the significance of that point is?
So that would be like having a propagator up to that time and that location of 180.
Yes.
And you mean what is the significance of this propagator quantity?
No, I mean just what that point signifies in relation to your original problem where you want to compute the entanglement entropy with respect to that x, right? Some other point.
Yeah.
Is there any meaning to that? Is it like is it that now that entropy?
So the statement is that somehow the entropy at x at this time can depend on the initial entropies of different regions at t equal to 0. But which one gives the most important contribution is determined by this minimization. But yeah, these different velocities are like the fact that information about the initial state from here can travel to the final state here.
If I just look at this dx to the minus d4 t times d bar y, that part of the that matrix element, is that roughly like saying so dy tells me how much entanglement, I mean, how sort of which sites are maximally entangled with each other, right?
Okay.
So I feel like that what dy is to be chosen sort of picks out some kind of a maximally mixed, not maximally mixed, some kind of state where various lattice sites are maximally mixed with each other. And that's of course to be determined dynamic. Is this roughly how 1 to be works? Can I think of these dy's as some kind of a state on your various lattice points where various sites are maximally entangled with each other?
You can think of it that way for the E state. So in particular, if you just took E everywhere, then that corresponds to taking an initial state here, which is the maximally mixed state.
Right.
But I don't know if you have a similar interpretation of eta as a state, as an initial state here, because it couples different copies.
Maximally mixed between A and A bars. It has maximal entanglement between A and A.
No, it has no. So it always has both of these have entanglement only within a single site, but different copies.
Different copies. Oh, I see.
So E is like maximally entangled between two copies, like the same forward and backward copy.
I see.
Yeah.
I and I plus 1.
So for that reason, I don't think we should think about the entanglement structure of dy itself.
Okay.
We should think of it as a tool for computing entanglement entropy of the initial state. Okay, so yeah, and then another thing which in the interest of time I won't go into in detail is like suppose like you wanted to more directly find a physical interpretation of this, then we can consider the setup that I mentioned where you have initial states with different initial entropy densities, and there was some growth rate gamma associated with initial state of entropy density S. And that can be more directly related to E, so that gamma of F and E evaluated at IS. Okay. So in particular, that means that for the dispersion relations that we find, the gap in the dispersion relation will determine the entanglement velocity, because that corresponds to S equal to 0, which is also K equal to 0. And then the the constraint on the memory intention is a constraint of the form E of I as equilibrium is equal to 0. So that is a sort of surprising constraint again from the perspective of hydrodynamics because it's constraining the dispersion. So firstly, the dispersion relation is gapped. And then even above the gap, we don't just care about small values of k, we care about some order 1 value of k and there's a non-trivial constraint. So somehow for entanglement entropy, if you were to formulate hydrodynamics, this should be true. Okay, okay. So the rest of the talk was supposed to be like showing some numerical results for more general cases. But we could also end here and I could say that it works more generally.
So for that, you would require this.
Yeah.
Right?
Yeah.
I mean, if it is not taking too long, then we can.
Okay, I can quickly go because it's mostly just showing plots which confirm these things. So
Please put down the next one.
Every excitation.
okay. Good. So what we considered so far was this second Renyi entropy case in the Brownian GUE model, and we derived this in the large Q limit by ignoring this term which causes the domain walls to split. So the rest of the talk will show that it's, this same structure holds more generally. So we'll consider finite Q in the Brownian GUE model, and then we'll consider the mixed field Ising model, and then we'll return to the GUE model and look at the third Renyi entropy, which is a bit more complicated than second Renyi. So okay, finite Q in the GUE model, we have this additional term which splits the domain walls. Okay, so now we could try to perturbatively deal with this 1 over Q squared, but a much better thing to do is to just directly numerically diagonalize, because we just have some spin 1/2 system, so we can diagonalize it on 12 or 14 sides. And then from that, we can get the momentum resolved dispersion relations. So this is what they look like. So in particular, in each case, for Q equal to 2 and higher, we see that there's still a gap in the dispersion relation. And the existence of the gap, even at finite Q, implies that the entanglement velocity is non-zero. But then there are still a couple of questions that remain. So firstly, we need to check that the structure of the eigenstates in this band is like what I said. So it looks like these locally dressed domain wall states. And in the Q equal to 2 case, things are a bit tricky because it looks like this one particle band is sort of merging into the continuum beyond some k. But the order 1 values of k were actually important for the evolution of the entropy. So we want to verify that for any k, this somehow, if the picture is robust for Q equal to 2, then there should still be a 1 particle band in this case. So we want to find some way to test that. So the way that we will do that is by using another numerical technique, which is developed for probing excitations of spin chain systems. So we'll start with some variational ansatz for the eigenstates, where you just assume that the kind of structure that I had said, you just assume it for some fixed delta. And then, so fixed delta, and then consider all possible choices of phi. So in this case, we have some Hilbert space of dimension 2 to the delta for these phi states. We consider arbitrary choices and minimize the expectation value of P4 in this set of states. Okay, so that gives us some upper bound on the energy of the excitations. And then as we increase delta, that upper bound will decrease. Okay, but if we find that as we increase delta, we find some rapid convergence of the dispersion relation, then that would tell us that we have a good approximation for our eigenstates with this ansatz. And it also gives us an independent estimate of the dispersion relation for this exact diagonalization. So this is a pretty standard technique in low energy physics in many body systems, used a lot by these authors. Okay, so let's apply this to the case of Q equal to 3, where we know that there is a well-defined band of single particle states. So, okay, so by doing that, we increase delta from 1 to 4, and we find that this curve changes very little. You can also see that more explicitly by doing some plot of log of differences in energy, the function of delta for each k, and you find that it looks like there's roughly exponential convergence. So that's good, and then we can also check that the one particle band that we're getting from this estimate agrees with the one particle band from the exact diagonalization. Okay, so this shows us that the structure of the eigenstates is indeed of the kind that we had said. But now let's consider the Q equal to 2 case, which was more confusing because of this merging into the multi-particle continuum. But even in this case, we see that beyond some value of delta, even for large K, there is a convergence of the dispersion relation. We can again see that more explicitly by plotting these differences. So that confirms that even in the Q equal to 2 case, this band sort of extends into the multi-particle continuum. And so even though these energies in the continuum are comparable to the one particle band, some of the final state only has overlap with states which look like are locally dressed domain one states. Okay, so this is confirming that for Q equal to 2, the picture is robust, which it should be because it's still some chaotic system just with lower onside Hilbert space dimension. Okay, and then so now we can use these numerically obtained dispersion relations to find the membrane tension. And we can do that by more specifically by sort of fitting the dispersion relation to some Fourier series and then numerically finding its the genre transform. And then that gives us these curves for the membrane tension, which in particular you can see satisfy all the constraints. Okay, and then yeah, let me not come. So yeah, okay, and you can see how it behaves as a function of Q. So you get some more data on what happens in this case. Okay, so that was for the GE model, but now let's consider this case where I have fixed couplings, this mixed field Ising form, and I can take these coupling coefficients to be some random numbers, and they each have their own strengths, which are these numbers. So in particular, I can fix the x and z values and then consider different values of gz. Okay, so one way that I'll try to probe robustness of this picture is that I'll change gz and then find that it remains robust for most values of gc. So the reason that this case is more complicated is that even though the ground state subspace still consists of these two states generically, except at gz equal to 0, which I'll mention later, the subspace spanned by up and down. Oh, sorry, I changed notation. So these ups are e's and downs are etas. But okay, the subspace spanned by then is no longer closed. So now I actually have a 2 to the 4 dimensional Hilbert space at each side, which makes it no longer possible to exactly diagonalize, but I can still use my variational technique up to delta equal to 3. Okay, so then I'll do the same thing. Now the phi has a different interpretation as a general state in this much larger Hilbert space. And then by doing the same procedure that I mentioned earlier, I find that again for values of gz other than 0, I find pretty good convergence of the dispersion relation. For gz equal to 0, it's a special case where I can write the Hamiltonian in a free Fermion form. So that case is not chaotic. And in that case, you can do a separate study of it, which was done in this paper, where you find that the gap vanishes and the ground state subspace is much larger. So that case should be kind of qualitatively different, and we see that the plots for the dispersion relation look different. And we can again find the membrane tensions from each of these curves for delta equal to 3. And we find that the ones from these cases, which are chaotic, satisfy the constraints, but then this delta equal to gz equal to 0 case, the dispersion relation that you get from here leads to a membrane tension which doesn't satisfy the constraints. Okay, so that is all consistent with what we expect. Okay, so let me briefly mention the case of the higher energy entropies. So now again, we have a complication. Even if we're just in the GE model, which preserves the subspace of permutations, now instead of a 2-dimensional Hilbert space, we have an n factorial dimensional Hilbert space at each side. And it turns out that if you like the relevant final condition is now etas, where eta is this 3 to 1 in the n equal to 3 case. And that actually does not evolve to a state that just consists of etas and e's. So you get all the other permutations in Sn by evolving this. So, okay, but now let's assume that the picture is essentially unchanged. And still assume that it has a form where it looks like eta and then locally dressed, and then has these. So now this is an arbitrary state which lives in an n factorial to the delta dimensional Hilbert space. And then for n equal to 3, I can use the same method as before up to delta equal to 4. And by doing that, I find that I get very good convergence again of the dispersion relation with delta. The convergence improves as I increase Q. Okay, and then that gives me, and then, because this delta of order 1 is still a good approximation, I can essentially plug into the formula for the nth Renyi entropy in the same way. I get essentially the same expression as before. And again, I get some relation between the growth rate for an initial state of entropy density S and the dispersion relation evaluated now at n-1 times IS. Okay, but now there is something a bit confusing which happens here.
Sorry, how did you give the fact that this state with the etas and the e's is not closed on devolution?
Oh, I dealt with it by saying that, let me assume that whatever other states I get are again restricted to a small region of size delta. But just assuming that is not enough, but then you can use this as a variational ansatz and then check that this is the dispersion relation is still converging with delta, so that's telling me that I get a.
But could it be that the nth Renyi will depend on the smaller Renyi and so on?
Good question. Yeah, well, I'll make a couple of comments on that.
Yeah.
But so far, not really, because this is just some independent dispersion relation. So it seems like for the third Renyi entropy, what I should do is plug into that dispersion relation, this k equal to this thing, like 2is. Okay. But then if I do that, I get something a bit disturbing because this is a function of s. Okay, so what I get is there are many things on this plot, but I just want you to look at the blue curve, which is what I get by plugging this, plugging k equal to this into the dispersion relation that I got on the previous plot. Okay, so the blue curve it should have the feature that if I start with the equilibrium state, the entropy doesn't grow. So at S equilibrium, the entropy growth rate should go to 0. Okay, and for comparison, the orange curve is what I get from plugging the relevant thing into the dispersion relation for the second Renyi entropy. Okay, which does sort of go to 0 at S equilibrium. So this is making an unphysical prediction that the third Renyi entropy has a non-trivial, has a non-zero growth rate even for the equilibrium state. Okay, so that is definitely wrong. And some of the way that has to get corrected is that we plugged in a particular family of eigenstates of the Hamiltonian into the evolution of the nth Renyi entropy, but somehow there must be corrections from some other family of eigenstates which give us the correct answer. Okay, and then this part is kind of a conjecture, but one scenario for how we could fix this is by noticing that this 3-2-1 can be seen as a composition of two transpositions. So it can be seen as 3-2 composed with 2-1. And these lowest energy eigenstates and one thing that you can check is that if you have two eigenstates, sigma and sigma tilde, that differ by a single transposition. So sigma is given by sigma tilde composed with some swap. Then the domain wall eigenstate between sigma and sigma tilde is still an eigenstate of P2n. Okay, so and that has the same dispersion relation as the second Renyi entropy, and that is needed somehow for consistency if you were to use P2n to calculate the second Renyi entropy. But anyway, so there are sort of individual eigenstates associated with domain walls between transpositions. And the state that we found where you had like eta and e pretty close to each other was like a bound state of these multiple transposition domain walls. But now, one possibility is that there could also be sort of unbound states of these domain walls where they're all propagating freely. And in that case, the energies would just be additive between the different domain walls. So you would get 2 times the second Renyi dispersion relation. Okay, so then that leads to some expression where in the growth of the third Renyi entropy, you have a competition between two terms. And then you just, to find the actual growth rate, you end up taking the minimum between these two curves. Okay, so that would predict some kind of first order phase transition in the membrane or in the function gamma as a function of S. And there are sort of, yeah, so I'll come into that in a minute. So in terms of the memory tension, you can find the memory tension from gamma by the Jordan transformation using these sort of general things that I'd written down before. So then you can see what function you get for epsilon v, and just by using the expression here, you find that this ends up having sort of two phase transitions as a function of velocity. So the first one is a first order transition, so the derivative jumps. And then the second one is a second order transition. And then after the second one, the memory tensions become the same for the second and third Renyi entropies. And so in particular, this means that VB is the same velocity for the second and third Renyi entropies. And actually, there is good reason to expect just independently from holography that maybe they should be the same for all.
All of them, yeah.
Because in holography, you can calculate the OTOC, which is like an n equal to 2 quantity. And you can calculate BB from that. And you can also calculate the memory tension for the von Neumann entropy and calculate BB from that. So von Neumann entropy is I'm going to one limit. So somehow both of those also agree with each other. So maybe somehow this is a generic thing, but I have no understanding of why physically, there must be some physical reason for this, but I don't know why.
So but in holography, I mean, Renyi entropies even for the vacuum state are different, it will depend on them. So what is this?
So no,
Why is the evolution somehow same?
no, their evolution is not the same. So in general, this function is different, right? So in particular, the entanglement velocity is different for the second and third Renyi entropy.
Okay.
But VB defined by this expression that epsilon prime VB is equal to 1, epsilon VB is equal to VB, that turns out to be the same.
No, but you expect that from holography. I'm asking why do you expect that?
Because of yeah, so
because simple quantities are different. So why do we expect this more intricate quantity to be same? That's what.
yeah, I expect that based on the following evidence that so Mark did a calculation of VB of the memory tension for the von Neumann entropy in holography, which was the n equal to 1 case. And then another thing you can do in holography is calculate the OTOC. So I didn't mention the case of the OTOC in this talk, but you can write the OTOC as in terms of u times u star times u times u star. So that's like an n equal to 2 quantity. And you can also write a formula for the OTOC in terms of these memory tensions. And yeah, so VB of the OTOC should be the VB for the second Renyi entropy. So somehow those two things turn out to match in holography.
I will just pointing out even doing the secondary entropy in some vacuum state is difficult.
Yeah.
But somehow thinking about it from OTOC point of view makes it accessible.
Yeah, somehow the OTOC calculation is easier than the calculation of secondary entropy in dynamical situations, but I don't understand exactly why.
Yeah. No, I mean even static situations are but go ahead, yeah.
Yeah, but so the evidence is based on VB calculation from OTOC, not secondary entropy. Yeah, so this is one thing that I would like to understand better. And then such phase transitions, there was some hint of them also from calculations in random circuits from a completely different calculation. Where they did some, but in that case, they were only able to comment on it in the case of large Q and also some large B expansion. But this is sort of confirming that this is a sort of robust thing, and there should be some universal mechanism for it. Okay, so good. So then this model, in this talk, we discussed Brownian models without conserved quantities and just showed that the memory picture is a result of the set of gapped low energy modes, which resemble fluid waves of domain walls between permutations. And then there are interesting questions about how this picture would generalize to the case of finite temperature. In particular, if you add some conserved quantities, then that turns out to be a very non-trivial interplay between the membrane dynamics and the dynamics of the charge density. So that's something that we're still trying to understand. And then you can also ask about how such a set of modes can emerge in systems without random averaging. So for this, one case you can consider is holographic CFTs. And we're starting to think about this with Marcus A and then Wang, just trying to actually do the calculation of Renyi entropy evolution in holography. Yeah, and then there are interesting questions about the phase transitions, higher dimensional case, and whether this can somehow be used to formulate some EFT of hydrodynamics for entanglement.
discussion in the talk. There is a urgent pressing question. If not, let's thank Shreya again.